Hey, good evening, class. So today we have our tutorial 6. So first we'll start with still solving nonlinear equation. But tonight we'll be looking at the second method, and that's the method that you are seeing here, right on the screen here. So it's called Newton-Raphson method. Okay. So let's look at this Newton-Raphson method here. So as you can see here, these are the steps of Newton-Raphson method. Shen Chun, there are 2 people in the waiting room. Okay, right. So there are 3 steps here, as you can see. So these are the 3 steps of the Newton-Raphson method. So let's go through the 3 steps. So we look at the first step here. Now, the first step here is to find this interval J that contains a root of the equation fx equal to 0. All right, so fx equal to 0 actually is the equation that we are solving. Now, this step here, this first step, if you remember, actually is the same as previously in our fixed point iteration method. It's the same first step, right? Can you see? Yeah, the first step is the same. Find this interval J that contains a root of the equation. And how we do that is that, that's what we did last week, right? So we are saying that we just, by trial and error, go and find some A, some B, and then go and get the value of FA and the value of FB. All right. So if one of them positive, one of them negative, meaning that the product is negative, that means there's an X star inside. Okay. So here, this is, for example, this is our point A. Then here is our point B. All right. Now, from the diagram that I draw here, I can see that my FA is negative, my FB is positive. All right. So important thing is one negative, one positive. So there's a root X star in between AB. Okay. Right. So that's the first step. So let's go and look at the second step. Now, the second step here, you notice that now here we just go and write down this Newton-Raphson method. Now, this formula is called Newton-Raphson method. All right. Xn plus 1 is Xn minus Fxn divided by F prime Xn. Okay, so just like this. And this formula is inside our exam appendix. So what do we do with this formula? Now, we need to go and choose X0 first. All right, so here X0 you need to choose. So you go and pick a X0 inside your interval J. Any point inside will do. Then you go and put inside. Then you go and calculate your X1, X2, and so on. Okay, and your all this X1, X2, and so on, it should converge to the solution. Okay. And then this step 3 here, that's actually the stopping criteria. Now, if you look at this step 3, stopping criteria, right? Suppose you want our answer to be correct to 3 decimal places. Then how do we do the checking? Well, actually, is we go and calculate this quantity, Fxn, absolute, divided by m. Now, of course, we have to go and pre-calculate the number m first, right? So this is actually our m. And then we go and check that this quantity, of course, this one is a question mark, right? This is a question mark here. Is it less than 0.5 times 10 to the power minus 3? Okay, if it is, that means your Xn is correct to 3 decimal places. If it is not, then that means we haven't reached the accuracy, and then we just carry on doing, and then also carry on checking. All right, so these are actually the 3 steps. And if you look at this step number 3 here, the stopping criteria, right? You will realize that actually it's the same as the fixed point iteration one. Realize this is the first step, right? Same. And then the stopping criteria here, that is also the same. Okay? Yep. So I think by now you also realize that our Newton-Raphson method only 3 steps, right? Whereas our fixed point iteration method, the one that we did last week, that one got 5 steps. So obviously this Newton-Raphson method is a simpler one. Okay. So let's go to our tutorial. Hey, let's look at our tutorial question here. So we want to use Newton-Raphson method. Okay, use Newton-Raphson method to solve these equations A and B here. And we want to give our answers correct to 3 decimal places. All right. Okay, so go through the steps. That means the 3 steps. And you know, our stopping criteria actually is the same as the fixed point iteration one, right? So we'll use the stopping criteria derived in last week's tutorial. Okay, the equations are actually the same as last week's. Same equation, just that we use different method to solve. Okay, so let's go and see here. Okay, here we are. Right. So this is our solution. Okay, so let's look at the part A here. So first of all, we notice that this equation here, well, that's not in the form of fx equal to 0, right? So what we do is we just bring it to this form, bring everything to one side so that we get fx equal to 0. So this is fx equal to 0. Okay, now you realize that the interval is actually given to us, right? So in last week's tutorial, we actually went to check already, right? Last week's tutorial, we already checked that there's a root inside this interval, okay? So we'll skip that step tonight, all right? Because we already did last week. So that means step 1 considered done, okay? So we have got the interval that contains a root of the equation. So now we'll go straight to the second step. So we are going to write down this Newton-Raphson method, right? Okay, right. So let's write this method down. So this is the method, right? Now, of course, you cannot just write like this. You got to put in your fxn, your f prime xn. Okay, that one is quite easy. Fxn meaning that your fx, you put the x as xn. Yeah, you can see, right? Then f prime xn meaning what? You take the derivative, you get f prime, and then you go and substitute the xn as your x. Okay, so this is what you have. All right, so until here, is everybody clear how to write down this one here? Everyone clear or not how to write down this one here? All right, so it's important, we must know how to write this down. Then after writing this down, then of course, you know, before we start, we should get the stopping criteria, right? Now, this stopping criteria, well, that is also from last week. Okay, so I'll just copy last week's stopping criteria. So this is the previous one. So last week we already calculated the small m. The small m is 4. Okay, so basically we want to check this. All right, so there's a question mark here. Okay, so we want to check, is this less than 0.5 times 10 to the power minus 3? Okay. So now we are going to tabulate our answer. Right, so let's tabulate our answer. And everybody can see my table on the right, on the left-hand side here, right? So this is how we can tabulate for Newton-Raphson method. So we will have the n column, the xn, that's where we put down our calculations, right? Then you see, put down your x1, you put down your x2, and so on, right? And then because of this, the fxn and the f prime xn, right? So we can also put in these 2 intermediate values. So you can have f prime xn, fxn. Then after that, you can substitute into here, and then you can get the next xn plus 1, right? Okay. And of course, this last column here, that's the stopping criteria. Okay, right. So if we follow this table format, so let's go and look at the next one. Okay, so here is our table, and I'm going to choose the same x0 as before, as when we did fixed point iteration method. All right, because I want to compare with the same x0, whether the convergence is faster or slower. Okay, compare both methods. So let's go and tabulate. So that's my tabulation, right? So you can see that I follow this one here. So I go and choose my x naught to be 1. So I do this calculation here. Now this one I skip, okay, because I don't think that it will be so accurate at the first try. So then I go and get my x1. Okay, so you see that not yet. And then I see that here, when we come to x2, we already got 0 point something times 10 to the power minus 4. Okay, and if you look at this number here, obviously it's less than 0.5 times 10 to the power minus 3, right? Yeah. And in fact, this number is even less than 0.5 times 10 to the power minus 4. Okay, so theoretically, it means that this number is actually correct to 4 decimal places. All right, but of course, we just need 3 decimal places. But what I'm saying is that this one, theoretically, is actually correct to 4 decimal places. Okay, right. So we can stop here. All right, so actually last week we say if you want this minus 3, right? So if we do until minus 4, that's quite safe already. So we can actually stop. So then we say that this x2, 1.028 is correct to 3 decimal places. All right, so that's what the question requires. Okay, and of course we say that this one is actually correct to 4 decimal places. Okay.
Right. Professor.
Yes.
Do we have to always start from the lower bound?
You mean to get this column here?
No. I mean your x0 is 1, right? So you start from the lower bound. Do we have to start from the lower?
It's actually up to you. Your x0 can be anything between 1 and 1.5. And why I choose 1? Anyone know why I choose 1 or not? Can guess why I choose 1? Can anyone guess why I pick 1 or not?
Easy to calculate.
Oh yes, because it's a simple number, so it's easy to calculate. You don't want to pick a number like 1.111111 like that, right? Also very difficult for you to press the calculator, right? So you just pick a simple number. Okay. All right. So look here, we notice that x2, x2 already give us the answer. Last week, I think last week I forgot, maybe until x4 or x5, right? Yeah, so certainly we can see that this Newton-Raphson method is faster. Is it okay? All right, so everybody clear, Okay, right. So let's go to some more summary, So now I'm going to polynomial interpolation. Okay, right. So polynomial interpolation. Right, so it's here. So this one is like that, right? So polynomial interpolation. So here we are given a set of n+1 points. I can see the points here, right? x0, f0, x1, f1, xn, fn. So there are n+1 points. All right. And our problem is to find what? Is to find this interpolating polynomial that passes through every point. All right, so you want to find a polynomial that passes through every point. So I believe here got something for me to draw, right? Okay, so that means something like this. So you got your points here, right? So you got your points here. Well, suppose I only draw 4 points. Yep. So then you want to get this polynomial that pass through these 4 points. All right. So that means your polynomial, so this is the point, right? Yep. And then, well, it's supposed to be a smooth polynomial. All right. Yep. So you can see that your polynomial passes through all the 4 points. Okay. And you want to find this polynomial. Yeah. So this polynomial here, usually we call it capital P. All right. And then there's a subscript also. Now the subscript is actually the degree of the polynomial. All right. So here what I draw here is 4 points, right? Yeah, I draw 4 points. So the degree of the polynomial, will be degree 3. Okay, so subscript 3. The degree is 1 less than the number of points. Okay, so it will be P3x. It's okay. So we want to find this P3x. Yeah, so everybody clear or not? So the problem is actually very simple. So we are given some points, right? Suppose given 4 points. Then you want to find this interpolating polynomial. And the degree of the polynomial is what? Is 1 less than the number of points. So in this case, it's a P3x. All right. So how to find it? Yeah, how to find it? So there are actually 2 ways of finding. So let me show you this first. So as what I mentioned, we want to find a polynomial Pnx of degree n that passes through every point. All right. Now this equation, that means you substitute SXXI, yeah, you're getting Fi, right? Yeah. So that means it passes through that point, yeah, right? Okay, so the meaning of this is it passes through all the n+1 points. Okay. All right. So now we want to find this polynomial, the Pnx, right? So in general, it's Pnx. So how do we find it? Now there are actually 2 ways to find it. So the first way is discovered by Lagrange. Okay, so he thought of this method. So that's called Lagrange interpolation. So if we follow his method, then we'll get this Lagrange. This is to honor him, right? So Lagrange interpolating polynomial Pnx of this function f. Right? The function f is actually unknown. Yeah. Okay, so this is what it looks like. So you see that Pnx is equal to what? Oh, it's equal to this. F0 L0 plus F1 L1 and then until Fn Ln. Okay. Now over here, your F0, F1 until Fn, these are actually known. All right, they are actually known values because they are actually the function values, the F0, F1 until Fn. So these are actually given. All right, so the values are known. And what is unknown here? Now, what is unknown here is actually the L0x, L1x, until the Lnx. All right, so all these L0, L1 until Lnx, these are unknown. All right, and therefore our job is actually to go and write down the L0x, L1x until Lnx. And once we have done that, it means you've got your L0, L1 until Ln already, right? Then you just put inside here and you get the Lagrange interpolating polynomial. Yeah, everybody clear or not? Okay, so therefore, now we go and see how to write down the L0x, L1x until Lnx. Okay, so we go to the next page here. All these L0, L1 until Lnx, they actually got a name. It's called Lagrange polynomial. All right, Lagrange polynomial. Now, if you don't be confused, this one is called Lagrange polynomial. All right, and then you thought, just now we also heard something like this, right? Well, actually not exactly. Just now that one is called Lagrange, and then interpolating polynomial. All right, so there's a Pnx. So you see, you got the word interpolating here, so that's different. Okay. So this one is just Lagrange polynomial. So these are the L0, L1 until Ln. All right. So first of all, we have that's how it is written. Okay. This expression is actually given in our exam appendix. All right. I'll come to this expression later. But first of all, we understand what is this Lagrange polynomial. All right. So actually, the property is up here. Okay, no, the property is not here. And I think the property is on the next page, is it? Yeah, I think so. No, sorry. The property of that is actually here. Okay. So this Lagrange polynomial actually it satisfies this. First of all, it is a polynomial of degree n. Okay, each one is polynomial of degree n. And when you substitute xi into Lj, the answer is only 1 and 0. Okay, it will be 1 if I and j are equal. Okay, and it will be 0 if I and j are different. Okay, so just like that. Yeah. So for example, this property actually means this. It means that suppose I have L, I mean the small L, these are L, it's not 1, okay? L0, yeah, L0. Suppose you got L0, you go and substitute X0. Then what will be the answer there, class? Suppose you got your L0X, right? You go and substitute in L0. What will this give you?
You get 1.
Yeah, it will give us 1. All right, let's see 0, 0 are the same, right? And if you have your, I want to type here. If you have L0, and then you go and put, for example, X1, X1, okay? So that will give you what? Still L0X, but you go and substitute the X1 inside. So what will this give you, according to
0?
Yeah, this is 0. So this is actually according to property 3. Is it okay? Yeah, so that's the meaning. So likewise, if I do one more, L in a small L, L0, if I go and substitute X2, X2, yeah, X2, then of course, you know, this is also 0. All right, and so on. Yeah. Okay, so because of this property, you know, this is a very nice property of Lagrange polynomial. So that's why, you know, when you say this is an interpolating polynomial, right? When you say this is an interpolating polynomial, you want to substitute. How about you substitute Pn? You want to substitute x0. Okay, suppose you substitute x0 inside. Now, if this one is the interpolating polynomial, you are supposed to get, you know, after all your calculation, you are supposed to get f0. Okay, because you have to pass through the point x0, f0, right? So if you substitute x0 inside, you are supposed to get f0. Okay, so let's see whether this expression, whether it gives you this or not. Okay, so what we do here is, you got your f0, okay, then you got your L0, and you go and substitute x0, right? Yeah, and then you got plus f1, and then your L1, and then you also substitute your x0, yeah, and so on. Okay, so everyone can imagine that, right? Yeah, so what do you get? And of course, your last term is Fn, and then you got your L0, and you substitute your x0. No, that is Ln, right? Yeah, Ln, and you substitute x0. Okay, so if you get this, you know, you go and do all this, then you realize that your L0 x0 is 1. So this term will give you 1. All right, so that means you get f0 times 1. Then here, your L1 x0, you know, L1 x0, what is L1 x0? L1, if you substitute x0, what do you get? Hey, class. What's this?
0.
Yeah, this one is going to be 0. Okay, so likewise, your Ln, you substitute x0, it's going to give you 0 also. So you see all the terms in between, they are going to give you 0. Only this term will give you 1. This term will give you 1. All right, so therefore, you will get f0. All right, so that's expected. So that is why, you know, this nice property of Lagrange polynomial will make sure that this Pnx written in this manner is really the interpolating polynomial. Right? Okay, any questions?
What do you mean by really interpolating polynomial?
Well, because what I write here is we say that this is an interpolating polynomial, right? So now we know the Lagrange polynomial, the property. So I actually show you that this is really the interpolating polynomial, right? Because you see, you substitute x0 inside, you get x0, right? And why you get all this is because of all this nice property of Lagrange polynomial, because of this property number 3. Okay. Yeah, I mean, this just to show you that this is really the interpolating polynomial. All right, so it does pass through every point.
So this step is showing that the line actually passed through all the points.
Yeah. Yes. It passed through every point. Yeah. Okay. So now we are convinced that this is a really interpolating polynomial. And why we put the name Lagrange in front? Well, this to honor Lagrange because he think of this method. Okay. So now we come back to here. Expression of Lagrange polynomial, right? So this expression, okay, yeah. So this expression is also taught by him. Yeah, so having this expression really will satisfy this property number 3. Okay, right. Now, this expression, if you see, actually is quite easy to remember, although it's in your exam appendix. You see, your LJX. Numerator is x minus x naught until x minus xj minus 1. And then you skip one term. Yeah, you skip the term x minus xj, right? And the next term is x minus xj plus 1, all the way until x minus xn. Okay. And then you see your denominator, also about the same. The difference is what? The difference is that here this is x, right? But the denominator is what? The denominator is xj. Can y'all see? Yeah, denominator is xj. Yeah, you can see, right? Okay, now this one, there's a long way of writing. So in short, you can write in this manner. Okay, everybody can see this pi, the symbol pi, right? This means product. Yeah, so that means product of x minus xk divided by xj minus xk. And then the product is what? K from 0 to n. So it means when you open up, it means this upstairs here. Okay, yeah. And of course, K from 0 to n, right? But we know that K cannot be J. Notice that there's no xj, right? Yeah. So that's what we have here. Okay. Well, there's a box here. This is actually my own interpretation. So how I interpret this is like that. Okay, so the numerator is x minus x naught until x minus xj without the term x minus xj. Right, you can see that there's no x minus xj, right? And the denominator is actually the numerator with x substituted by xj. Yeah, so that's it. Okay, all right now. Yeah, so I think we got this Lagrange polynomial already. I think now we can go and do one problem. Right, so we are here. So let's look at number 2a. No. Where's my question? My question is here. Okay, let's look at 2a here. So here we actually got 2 tables here. All right. For each of them, we want to do Lagrange interpolating polynomial. So you notice that there are some points given, right? So you want to do the Lagrange interpolating polynomial. Okay, so we'll do this one first. Okay, and we'll be doing this table A. So this is our table A here. Okay, Lagrange polynomial. This is the one, right? Lagrange polynomial. This is our problem, right? So first of all, we should decide how many points are given to us. How many points are given to us? Yeah, class. How many points are given? Hey, class, what do you think?
3.
3. 3 points. 3 points or 4 points?
4.
4. Question mark also counted or not? And you see here, 0.4, this one question mark. Is it counted one given? Not counted. Okay, so question mark means the point is not given. All right, so actually what is given is just 3 points. All right, so we are given 3 points. So given 3 points, so what is your PNX? What is the degree of the polynomial? Yeah, class, you are given 3 points. So what is the degree of your polynomial, your PNX? What is your N?
2.
Class?
2 points.
N is 2. All right. So N is 2. Is okay? 3 points, degree is 2. The PNX, the degree is 2. So meaning that you are looking at P2X. Okay, first of all, we got our points here. Let's go and call it X0, F0, X1, F1, and so on. So this one very easy. So you see your N is 2, right? So we have X0, F0, X1, F1, X2, F2. All right, so this okay. So now we want to do Lagrange interpolating polynomial. Lagrange. Okay, this one is the Lagrange one. Lagrange one. Okay. So let me write down Lagrange. So Lagrange one will be what? F0, L0, X, F1, L1, X. You're looking at P2, right? So what is your last term, class? For P2X, Lagrange polynomial, what is your last term? You got F0, L0. What's your last term?
F2, L2X.
Yeah. So your last term, N is 2, right? So your last term will be F2, L2X. Okay, so that means you need to write down your L0X, L1X until L2X. Okay, so that's why you see here, I'm writing down my L0X, L1X, L2X. So these are my Lagrange polynomial that I need to write down, right? Okay, so let's so let's go and write this down. Okay, so wow, you're looking at the formula here. So let me go and write down. Yeah, let me go and write down. So let's write down together. Okay, so let me write down this L0X. Okay, let me write down this L0X. Now it is L0X. That means your numerator is without the term x minus x0. Okay, so that means you can only start with x minus x1. Is it okay? Then the next term is x minus x2. All right, that's all. Are y'all okay here? Yeah, this okay? Everybody okay? For L0x, this is the numerator. All right, and then your denominator, denominator, now if you look here, it's actually numerator with x equal to xj. Now in our case, the j is 0. So that means x0 minus x1, then x0 minus x2. Are you okay here, class? All right now. Class, are you okay here? Everybody know how to write down? All right. Okay, how about you tell me how to write this down? Suppose we go and do L1 now. L1, what's the numerator? Anyone can give me the first term, numerator?
X minus xo multiplied by x minus x2.
Yep, correct. Yeah, because you cannot have the term x minus x1, right? Yeah, so x2. Okay, right. How about denominator? Denominator is what? Your x in your numerator, you are going to substitute what? Yeah, class. Numerator. I mean the denominator is numerator with x equal to what?
xj.
Yeah, xj, but what is your j here?
1.
Yeah, that's right. So you should put x1, then minus your x0, okay, and then x1 minus your x2. All right, so this is your L1x. All right, so I hope everybody is okay. Yeah, know how to write this down. So this is how we have it. Oh, so like that, then like this, and then like this. Okay, all right, yeah. And then of course you go and put in your x0, x1, x2, like that. Here no need to multiply out, just put it like this. Okay, so now you are ready to write down your Lagrange polynomial, interpolating polynomial. So that's your f0, L0, f1, L1, f2, L2, right? Okay, now your f0, f1, f2, of course, these are given. All right, so you are going to multiply your f0 with your L0. Okay, so this constant and the denominator, well, only that one you simplify. Okay, yeah, that's why you get to this number here. And then this one, you see that I don't multiply out. Yeah, just leave it like this. Okay, so this is Lagrange interpolating polynomial already. Any questions, class? It's like no problem, Okay, then let's look at the next question. Okay, the next question is actually another way of writing the interpolating polynomial. So should we go and do that? Yeah, why not? So let's go and do that. So let's go and do this Newton's divided difference interpolating polynomial. All right, this one, Newton's divided difference interpolating polynomial, is actually another way of writing the interpolating polynomial. All right, and you can see the name in front, right? Newton. So it's actually developed by Newton. Okay, so maybe we go to this Newton. Let's see, Newton's divided difference interpolating polynomial. The problem is the same. You still have your n+1 points, and you still want to find this interpolating polynomial that passes through all the points. All right. So, well, you still have your Pnx, but this time, we are going to use divided difference to do it. Okay. Let me show you the final expression. So this is the Newton's divided difference interpolating polynomial Pnx of the function f. Right. So this is the expression. Pnx equal to fx0 plus x minus x0 times this. You see this thing, right? It's actually divided difference. And then plus this one times this. This one is actually divided difference. And then the last term is like that. And this is also divided difference. Okay. And this method is actually developed by Newton. So that's why we call it Newton's divided difference interpolating polynomial. Is it okay? All right. So of course, to do this method, I mean to write down this Pnx, we need to find the divided difference, because you see all these are divided differences, right? So unless you know what it is, otherwise you cannot write, right? So let's go and find the divided differences. Okay, here, let's look at this table here. This is what we call divided difference table. All right. So every time you want to do divided difference, you must do a table like that. Okay. Now, first of all, how you do this table is like this. Now, of course, this one is just an example. It's showing us 4 points. You see your x0, fx0, x1, fx1. You can see there are 4 points here, right? So this is the table for 4 points. Now, of course, if it is 5 points, 6 points, then you also know how to do, right? Yeah, you just expand the table. Table just become bigger. Okay. This is my x. This is my fx. So actually, the first 2 columns are given. The numbers are given. All right. Now, from here onwards, this is a divided difference already. It's actually called first divided difference. Then the next column is actually called second order divided difference. Okay, and this one is called third order divided difference. Is okay? So it's like that. Okay, now if you look at the divided difference, before we talk about how to do, and you realize that you see here every number, every entry got a number, right? But when you come to first divided difference, you realize that the first entry is blank. All right, so you only get 3 numbers left. Then when you come to second order, now only two numbers left. And you only start from here, right? And when you come to third order, you only got 1 number left. All right, so how we do this table is like that. As I say, well, depending on how many points you are given, right? So maybe your table is bigger or your table is smaller than this. But what you do is that you just do until you are left with 1 number. Okay, you do until you are left with 1 number, because you can't do further, right? Because if you do further, that means no number left, empty. Okay, so you just do until you are left with 1 number. Everybody clear? Okay, all right, then the next thing is, now you realize that the diagonal of the table are highlighted. You see, this is what we call diagonal of the table, highlighted, right? This highlighted one, the diagonal of the table, actually is very important. Why important? Because all these numbers, they are used in PNX. I show you the just now expression, right? You see here, f(x0), f(x0), x1, and the third one is this, right? And the last one is this, right? So all these numbers, they are actually on the diagonal of the table. This one, this one, this one, this one. You see? So therefore, if we can, go and do up this table, then actually we get all the values. Okay, all right. So now, of course, now we come to the important part. Actually, how do we do up the table, right? Yeah, how do we do up the table? I see I got a blank table here. Is to show you how we do it. Okay, let's do some typing here. So this is your number f(x0), f(x1), f(x2), and so on, right? Let me call this 1. No. Maybe I will call this 0. This is for me to write easier later on. It doesn't mean it's 0. It's just a notation. So this number I call 0, call this 1, call this 2, call this 3. All right. Now, how do I write down this number here? How do I write down this number here? Now, according to definition of divided difference, this number is 1 minus 0. That means this minus this. And then I should put bracket. 1 minus 0. And then divide by, divide by what? Divide by x1 minus x0. Okay, yeah, so it's like that. Everybody okay? So this is the number 1 minus 0 divided by x1 minus x0. Okay. The others are also like that. They got a pattern. Okay, so this will be 2 minus 1. Yeah, over, I think you can guess, right? x2 minus x1. Yeah, can you see the pattern? I hope you see the pattern. Hey, then now how about you tell me what is this? How to write down this? Yeah, class, how to write this there? What is the numerator?
3 minus 2.
3 minus 2. Okay, meaning that this number minus this number. And then over what?
X3 minus x2.
Yeah, that's right. Okay, so you see, it's actually quite easy to write down these values, right? Okay, right. So now, based on these 3, we can now go and do the second order divided difference. All right, so let me call this. Let me call this 0, 1, 2, 3. Maybe I call this 4. And then this one I call it 5. And this entry here, let me call it 6. So 1, 2, 3, 4, 5, 6. Yeah. Okay, so this is 4, this is 5, this is 6, just a notation. Okay, so easier for me to write. Okay, so when I do here, I should start from this entry here. Okay, so let me show you the first one. I will take 5 minus 4. Okay, this number minus this number, and then divide by x2 minus, is it x1? x2 minus x1.
x0?
Yes, it's actually x0, it's not x1. Okay, so we realize that just now, in the column before, this is first order, right? You realize that the x is just one step, right? x1 minus x0, x2 minus x1, x3 minus x2. But now, because now we are doing second order, so now your x is actually 2 steps. So x2 minus x0. Okay, yep. So let me call this 7. Okay, this number I call it 7. Okay, now I go and fill up this. How about you tell me what is this? What is this? How to find this value? This is what?
You get 6 minus 5.
Yeah.
And then you get the x3 minus by x1.
Yes. Yeah, jump 2 steps. So that's why it's x3 minus x1. Okay, so this is how you get this number. We call this 8. All right. Wow, and you see, wow, this is the last column because you know that these 2 numbers will give you this last entry here. All right, so what is this? Hey, you tell me how to get this. What is this?
8 and 7.
8 minus 7.
And you get x3 minus by x0.
x3 minus, wow, this time jump 3 steps. So that's why it's x3 minus x0. Everybody clear or not? You see here, jump, the x is 1 step. Here, your x 2 steps. Then here, your x is 3 steps. So x3 minus x0. All right. So as you can see, actually it's quite easy to construct this divided difference table. All right. Although it looks like, initially look like, well, I don't know how to do, right? But now actually it's very easy to do. Okay, so let's go to our problem. Let's go to our problem. Yeah, our problem. That's our problem, right? We are doing part A, right? And we say we are looking for P2X, right? So let's go and see our Newton's divided difference interpolating polynomial. So this is our P2X, right? So that means our n is 2. So we'll have fx0 and so on. And we want to know what is your last term, right? So you just look at your last term here. X minus x0 until x minus x. 2 minus 1. 2 minus 1 is what? That means x1, right? And this is x0, x1, and your n is 2, right? x2. All right, so you know that this is your last term. Is that okay? So it will be just these 3 terms. Okay, now. Okay, let's go and do our divided difference table. This is our points. Okay, so let's go and do the table. So this is actually our table. So this is our x0, this is our fx0, right? Yeah. So we only got like that. So you see our table here is smaller. Because just now I show you one is 4 points, right? But here only 3 points. So you see very fast, then we come to only 1 entry here. All right. Okay. Now you see our page actually very colorful. You see this fx0 is green. It is actually this. This one, your first order divide difference is what? Beige color, right? It's actually this entry. And this one, is your pink. The pink one is a second order divide difference. It's actually this number, right? You see, this one is this one is this one is this. All right, so isn't it very easy? All right, then you just go and put in all. Okay, any questions? Okay, looks like no problem, right? Okay, so then the next thing is we come to the missing value. Okay, let's do the third part now. We want to do the missing value. Hey, missing value. Missing value. Now, what missing value are we talking about? I see in this table, can you all see there's this question mark here, missing value. All right, so we want to find this missing value. Actually, this is the application of interpolating polynomial. Interpolating polynomial, it actually is for you to estimate the function value at some x, okay, and the x is within the range of interpolation, okay. And here they interpolate from 0.2 to 0.7, right? So you see 0.4 is somewhere inside, right? So now you want to estimate what is sine 0.4. Well, assuming that we have no calculator. Okay, so what we do is very simple. You just approximate by sine 0.2, right? Yeah, so your function will be approximated by P and X. Is it okay? So this is an application of interpolating polynomial. You will just approximate the unknown function by this P and X by the interpolating polynomial. All right. So therefore, if you want to find sine 0.4, right? Yeah, you want to get sine 0.4. That means your function value at 0.4. So what we do here is we take our P2x. Yeah, we take our P2x. Then your x, you go and substitute. Substitute what now, class? Class, substitute what? Your P2x, your x, you want to substitute what? Yeah, class, anyone?
0.4 maybe?
Yeah, that's right. Just go and substitute 0.4. And that will give you an estimate value of sine 0.4. Is it okay? Yeah, let's see. Your P2x here, right? Then you just go and substitute 0.4. Okay, so that's what we do here. Missing value, the sine 0.4. Yeah, so this is the value. Okay, now of course here P2x, just now we actually calculate P2x using two different methods, right? Lagrange and Newton. So here, if you ask me which one to substitute, well, either one will do, because both of them are actually the same. All right, both of them are actually the same. So in fact, this is not here. It's tabulated here. I mean, it's mentioned here. That's our point 2 here. The Lagrange interpolating polynomial and the Newton's divided difference interpolating polynomial, although they look different, but they give you the same P and X. Okay, look different, but they are actually the same. All right, so this P and X is actually unique. Yeah, it's unique. So no matter what method you use, you will get the same answer. If you go and multiply out everything. Okay, not? Okay, right? Yep. And then,
Professor.
Yeah.
So the P and X actually pass through all the points, right?
Yeah, correct.
But when it passed through all the points, but why is it still an approximation?
This one, then, because, well, you cannot just say pass through all the points means it's equal to fx, what? Because it only passed through a sample of points, right?
Only the sample.
Yeah, because it's only n plus 1 points, right? But you know that for the function, actually it's an infinite number of points, right? So it only passes through n plus 1 points. So you cannot say it is fx.
So it's not all the points, just sample points.
No, what I mean is that it passes through all the given points.
Oh, all right.
It's through all the given points, but then the given points is only 4 points, right? 4 points, you cannot say is equal to fx, right? You only coincide with fx at these 4 points.
All right.
Yeah. Oh, okay. Then of course now it comes to the question that now you got two expressions, two P2X, right? One, I mean, they are done by different methods. So then I'll ask you, actually, which method is more efficient? Class, which method is more efficient? What?
Newton.
Yes. Newton. Okay, so you all watch the video, right? So the video one shows what? Newton one is more efficient. More efficient. All right. You all know why more efficient or not? Well, it's because, you know, Newton sit under what tree? Newton sit under what tree? Newton sat under apple tree. Yeah. And then Lagrange? Lagrange?
Durian tree.
Oh, yeah. And you all know what is durian tree, right? Yeah. Durian tree. Have you all eaten durian before? Hey, class?
Is that really what happened?
What do you think?
I don't think there's any durian tree in Europe.
There's no durian tree in Europe. Wow, that one.
I'm not sure, but I don't know.
That remains to be seen. I'm not very sure whether there's a durian tree in Europe or not. Or maybe Lagrange, he came to Southeast Asia and then he sit under this durian tree, right? Yeah. Because now we got this VTL already, right? So this Lagrange, he can actually travel to Singapore and then sit under this durian tree, right? Yeah. Yeah. So actually, of course, this one is just a story. Yeah. So sitting under apple tree actually is a very good thing, right? So you can discover gravity, right? But if you sit under durian tree, then the durian drop. Well, if durian drop onto your head, I think got a big problem. So need to go to hospital, right? Yeah. Well, so this is actually just a story. So actually, it's just to say that Newton's method actually is a smarter method. All right, it's actually a smarter method. So maybe I explain why Newton's method is a smarter method. Okay, everybody is looking at this Newton's divided difference, the P and X here, right? So suppose we add one more point, okay, and that point is X. So now it should be n plus 1. Yep. Yeah, n plus 1. And then, of course, the function value is also n plus 1. Okay, so that means you add one more point. So if you add one more point, and then you still want to find this P and X, right? Interpolating polynomial, then you should be looking at P n plus 1x. Okay, because now you've got one more point. All right, so your degree of the polynomial will have to increase by 1. All right, and then if you look at this Newton's the formula, this one is your P and X, right? So you can actually see that it actually also the same one, right? All these terms all will still be the same. So basically, you can take the P and X. You can take the whole P and X, right? Then you just add one more term, because you know that the last term, now this is not the last term. So the last term is actually x minus x naught, x minus x1, then dot, and the last one will be x minus, anyone want to tell me x minus what? The last one here is what? Hey, class? No? Now this one is not the last term. So for Pn plus 1x, this will be x minus x. What's that? The last term? X minus x naught, x minus x1, and the last term here should be x minus x. X what? It should be xn, right? Yeah, follow the pattern. Okay, and then followed by the divided difference. which is x0, x1, and until, okay, can you give me this last number here? X what? Anyone?
Is it n plus 1?
Yes. Yeah, so it should be this. Okay, so it's actually like this. So your Pn plus 1x is actually your Pnx and then plus all this. And then you realize that, oh, so that means your earlier, your Pnx, you can just put in here, right? And then you just go and add this term only. All right, and adding this term only means what? Means you must go and find this divided difference. Okay, and how do you do the divided difference? You just go to your table, then it's your table, right? Or maybe I put it here. No, this one a bit troublesome, huh? So that means maybe if we take this as our example, then you just add one more point here, x4, and you have your fx4, yeah. And then this one you can calculate or not? You can calculate, right? Yeah. So this one you can calculate, and this one you can also calculate, and this one, the entry here you can calculate or not? Yeah, can. You can calculate just by using the same method, right? Then when you reach here, that time you realize that, oh, now you've got two numbers here. So meaning what? Meaning that you must add one more term, one more column, right? And then go and calculate this number, right? Yeah, you go and calculate this number. And this number here, your last number here, the one that you calculate here, will then be this value. Okay, this last value. All right. So is it difficult to get this last value? Actually, also not say difficult. You just go and expand the table only, right? Okay, yeah. So this is Newton's method when you are adding one additional point. Now, how about Lagrange? Lagrange one, is it also like that or not? Equal to Lagrange polynomial. Okay, Lagrange polynomial is here. Let me go and remove all this. Let me remove all these things. Can I remove all this? Okay, so suppose here we also add one more point, right? So then you know, oh, I also need this m plus 1, right? And then x, okay? So if we follow this Lagrange interpolating polynomial, then looks like it's also f0, L0, f1, L1 plus fn, Ln. So you still have f0, L0, f0, L0, and then plus f1, and then L1, and then plus, and then plus and then plus, and of course you still have your fn, and then Ln, yeah. But of course we know this is not the last term, right? There should be one last term, which is f, and the subscript here will be m plus 1, yeah. And then of course our Lagrange interpolating polynomial, you also got this m plus 1. Okay, all right, so it looks like it's like this. So this is our Lagrange interpolating polynomial when you add one more point. All right, then if you look at this, then you compare with this. Then you say, hey, then like that also the same one. Then this is also Pnx, right? It's just Pnx, right? And then, I always type the wrong thing. It's just Pnx and then plus this last term, isn't it? So is it like that, L n plus 1. Okay, so is it really like this? Is it like that? Is it also just Pnx, then just plus this only? And then you see, that's also very simple. Then you just go and write down your Ln plus 1x. Just go and write down your Ln plus 1x only. So is it also so simple? Class, what do you think? Is it as simple as what I've written?
No.
Actually, it's no. All right, why no? Well, that's because of the definition of the L0, L1, Ln. All right, you just look at the expression. You realize the expression is what? X minus x naught until x minus xn. Yeah, that is if your last point is xn. But if your last point is not xn, that means you will have until multiply until x minus xn plus 1. You realize that? So that means our previous, all these things that we write down, your L0, your L1 until your Ln, they are different from the earlier L0, L1 until Ln. They are different. All right, so they are different. So that means this is not equal. Yeah, it's not as simple as this. All right, so that means your L0, L1, your Ln, and of course your Ln plus 1, you have to write them all again. All right, you have to write them all afresh. You have to calculate again. All right, so that's why you see, wow, looks like got more effort involved. Yeah, so that's the reason why we say that if one more point is added, then actually Newton's divided difference is more efficient to handle the situation. Lagrange one is very troublesome. It's like you're getting a totally new problem. Okay, you got to rewrite everything. Okay, so I hope you understand what I'm saying here. Okay. Right. So this one done, So let me go to the last part of the question. Now, last part of question is actually to get this upper estimate for the error. Okay. Now, what's the meaning? Upper estimate for the error. Now, just now we found this missing value, right? So actually, it's an approximate value. It's not exact. This 0.39 something is just approximate. All right. So what we do here is because it's approximate, right? So there's an error. So you want to get an upper estimate of the error. Okay. So let's see how we do that. So this is about error estimate. So this is a theorem called error estimate. Yeah. And this error estimate here, you notice that the left-hand side is what? Fx minus Pnx, right? So this Pnx here, it can be the one calculated from Lagrange, okay, or it can be the one calculated from Newton. Okay, both are also applicable. So this formula, this error estimate is applicable to both Pnx. All right, now? Okay, yeah, right. So now let's look at this. So suppose your f is n plus 1 times continuously differentiable. Then your fx minus Pnx. So this is like what? Like absolute error, right? Yeah, don't you think so? This is like absolute error. Absolute error. Yeah, so this fx minus Pnx is like absolute error, right? So Sm equal to what? 1 over n plus 1 factorial, and then you've got this product here, x minus x0 multiply all the way until x minus xn, and then times this thing. Now this thing looks long, right? But actually it's just the maximum of the n plus 1 derivative of f at xi. This thing is called xi. Okay, let me spell for you xi. That's the symbol. You know, when I type this is the command that I use. So this is called xi. Yeah. So this xi is between the minimum of x and all the xi, the maximum of x and all the xi. Okay, so it's just like this. So this is upper estimate for the absolute error. Okay, now. And then of course, another thing I want to point out is now you see all the x I go and highlight, right? This one, x, highlight. This x also. Here the x, here the x. What's the meaning? Why do I highlight that? Why do I highlight? Got any meaning or not? Yeah, class, any meaning?
They're the same variable?
No, not same variable. they are the same value. They are the same value, x. This x, this x, this x, they are the same value, x, same value. It's okay? All right, yeah? Yeah. Okay, so now I'm going to apply this to our problem, right? Well, this is our problem, right? You want to find the error estimate, right? Maybe I go to the beginning of the problem. So this is a table, right? Yep. So I want to find out the error estimate, right? Sine 0.4. Sine 0.4. So my function here is my function here actually is fx. So here we realize that our function is actually is sine x. Okay. All right. So let's go and draw. Go and write down this error estimate. Hey, just write this down. So absolute value fx. We are looking at sine 0.4, right? So sine 0.4. So meaning that the x value here is 0.4. Okay, so that is the x value of interest. And then you want to minus off absolute value, right? P and x. Now ours is P2, subscript 2, and then x. So my x is 0.4. So this is actually the approximate value, isn't it? Yeah. So this one, your fx, meaning exact value, and your P2 0.4 there is actually the approximate value. So this is our absolute error. Okay, less than or equal to 1 over n plus 1 factorial. Can you tell me what is n plus 1 factorial here, class? What is our n here? Class, what is our n here? What is the n in this case? What is our n in this problem?
2.
Yes. So n plus 1 factorial meaning 3 factorial. Okay. All right. And then you got this product term. Well, there is x minus x naught. The x is 0.4, right? 0.4 minus x naught. Okay. Of course, the x naught value you know, right? Later on you can put in 0.4 minus x1. So until xn, right? 0.4 minus x2. Okay, right. All right, so that's the product. And then I want to multiply the maximum of this thing, right? So maximum, well, there's a subscript. So the subscript here is my xi. Well, I don't know how to type xi. Oh yeah, xi is this one, right? Xi is between, well, I think I need my xi here. Xi is between what number and what number? Less than or equal to what? And greater or equal to what? Yep. Okay, so I need the two values there. Okay, and then of course I want the n plus 1 derivative. N plus 1. That means third derivative, right? Yep. So the third derivative of the function f at xi. Oh, well, is there a place for me to put? Maybe I should bring this down. Okay, like that. Okay, so well, I haven't filled up the xi, the range for xi yet. So let's take a look. Minimum of x and all the xi, maximum of x and all the xi. So the x, you know, is 0.4, right? So your x0, x1, x2 actually are all here. Is your x0, 0.2. 0.5 is your x1, 0.7 is your x2, right? And this is your x is 0.4. Okay, so basically it's the minimum of from 0.2 to 0.7, and of course the maximum, right? So what's the minimum? 0.2, 0.4, 0.5, 0.7. The minimum is what? What's the minimum? 0.2, 0.4, 0.5, 0.7. The minimum is what? What's the minimum value?
0.2.
0.2.
Yep. So it's 0.2. And then of course the maximum value here is 0.7. All right, so here you are maximizing the third derivative of the function over the interval 0.2 to 0.7. All right, so that's what we have. All right, so notice that we write this down according to this theorem. Okay, let's go and see our solution. Okay, so this is our solution, right? Okay, so looks like here, here in front, all we know how to put in, right? No problem, just that this maximum, we need to go and find the third derivative. Yep, so let's go and do that. Third derivative of the function, sine you differentiate 3 times, okay? You take absolute value and you maximize over this interval. Okay, so cosine. Cosine function maximize over this interval. Wow, here I put cosine 0.2. Why is that so? Maybe this one I explain a little bit. Cosine function. Cosine function is like this. It is like that. Okay, like that. 1 cycle. This is 2 pi. 2 pi. All right. Yeah, and of course this one is 0. 1 cycle. Okay. Now when it involves this triple function, the unit default unit is radian. So here 0.2 to 0.7, meaning from 0.2 to 0.7 radian. Okay. Yeah. So you're looking at 0.2 to 0.7. Now this point here, you know, this point that I'm marking here, this one, when cosine is 0, this point is actually pi over 2. Right, this point is actually pi over 2. Do you all know what is pi over 2? Yeah, class, do you all know what is pi over 2? Class, do you all know what is the value of pi over 2?
0.
No. I mean pi divided by 2 is what value?
Oh,
Pi divided by 2 is what value?
90 degrees.
I mean in degree.
No. I mean pi, you all know what is pi, right?
Yes.
Yeah, 3 point something.
So if you divide by 2, you should get
1.5.
Maybe 1.5 or what lah, right? So here we are only looking at 0.2 to 0.7. So if this one is 1.5, so that means your 0.2 to 0.7 should be somewhere here, right? Should be, the interval should be here, right? Because this is already 1.5, so should be here. All right. So if you look at this portion of cosine, all right, this is a portion, right? Yep. You can see that it is positive. One thing is positive. Well, anyway, you're taking absolute value, right? So it's just this part. And also in this interval, your cosine is increasing or decreasing?
Decreasing.
Well, I need here sing. Don't know what sing.
Decreasing.
Yes, decreasing. It's decreasing, right? So if you want the maximum, where's the maximum? Do you think it's at 0.2 or at 0.7? It's very clear that it's going to be at 0.2, right? It's very clear from the diagram, right? 0.2 is here, 0.7 is here, right? So the maximum is at 0.2. All right, so that's why you get this. Okay, all right, all. Okay, so you got this already. And then now this is what I wrote down here earlier on. I typed here, right? So you can see that exactly the same. So now this number here, you can put in your cosine 0.2. Okay, you go and put in your cosine 0.2. And you calculate, then you get this number. Okay, yep. Then you want to see this is less than 0.5 times 10 to the power of what? Less than 0.5 times 10 to the power of what? Okay, power of what? How to see? Actually, here you are looking at, you want it to be less than, behind should be a 5, right? So maybe I go and change the color, change to a red color. Okay. So remember, you want to put a 5 behind. All right. Do you think if I put a 5 here, That means less than 0.5 times 10 to the power of 0. Do you think it's good? No, two loops. All right, you want it to be as tight as possible. All right, so you are trying to put your 5 as late as possible. So maybe you put 0 here. Do you think I need to put a 5 now, or I can still delay putting the 5? Basically, I want this to be less than. Okay, less than. Yeah. Less than. Do you think I need to put the 5 here, or I can still delay? Maybe you can still delay. All right, maybe you can still delay. Okay. So if I still delay, do you think I need to put a 5 here? Or can I still delay? Okay, if I still delay, I still put a 0 here, and then I put a 5 here. Do you think it makes sense? 0.00098. Is it less than 0.0005? You go through your brain, you think this one correct or not? Is this correct?
Don't think so.
This one is not correct, right? This one wrong already. So then you know, hey, you're wrong already. What happened now? That means you put your 5 too late. So just now you cannot put 0, you must already put the 5. So this is the latest that you need to put the 5. All right, and then from here, then now you can tell from here, you want to write in this form. Okay, can you tell me? This is 0.005, is 0.5 times 10 to the power of what? Times 10 to the power of what? Yeah, 0.05 is 0.5 times 10 to the power of what?
10 to the power of 2.
Yeah, so actually this one is 2. Okay, so therefore you got it already. It's less than 0.5 times 10 to the power of minus 10 to the power minus 2. And now you can draw a conclusion. Your this one is absolute value. Your this one is absolute value. Sorry, absolute error. Absolute error. Okay, absolute error, there's this part here, less than 0.5 times 10 to the power minus 2. All right, so what does it mean? So it means that your approximate value is correct to 2 decimal places. Okay, so this 2 here, this 2 here, I cannot highlight here. I'm not able to highlight there. The 2 here, okay, actually is this 2. Okay, all right. Cannot class. Okay, yep. Right, so this one done already. So we actually completed the whole question. Okay, so let us now go to another concept. So we completed this interpolation, polynomial interpolation. All right, and we'll now go to the concept of least squares approximation. Okay, least squares approximation. Okay, least square approximation is different from polynomial interpolation. What's the difference there? Is that it doesn't have to pass through all the points given. All right, it's unlike polynomial interpolation. Now, just now interpolation, polynomial interpolation, right? We say the P and X must pass through every point. All right, but the least square approximation is not. It doesn't have to pass through every point. Right, so if we say we go and draw a diagram here, say these are the points given. So we got 1 point here, another point here, another point here, then maybe another point here. All right, so these are the 4 points, and then you want to well, there's some unknown function here, right? And then you want to approximate it. Now, how do you approximate it there? That is your least square approximation. So for example, you say you want to get a least square straight line. All right, so that means you want to draw a straight line. Now, how you join this by a straight line? One straight line, okay? So then you look. And then you think, oh, my straight line is like that one. Okay, so imagine this is your straight line. Yeah, so you say, oh, this is my least square straight line. Least square straight line meaning that we call it P subscript 1 x, okay, degree 1. So that's P1x. So this is our least square straight line. Okay, least square straight line. Straight line. Yeah, so this is our least square straight line. All right, so if you look at your least square straight line, actually this is what you all do, right? When you're doing a physics experiment, all your experiment, then you go and draw this kind of thing, right? So actually you're drawing this square straight line. All right, so you realize that your least square straight line actually doesn't have to pass through all the points. So in fact, what I draw here is it doesn't pass through any point. All right, it's not saying need not pass through all the points, but what I mean is that it doesn't have to pass through all the points. All right, but of course it can pass through some of the points. Is it okay? Okay, yeah. So this is your least square straight line. So actually our least square straight line, how we draw this there? Why I draw like that? I don't draw some other straight line. How come in my straight line I don't go and draw, for example, why I don't draw like that? Why I don't say that, oh, this is my least square straight line? Then why my least square straight line is like this? So that's because we are looking at some kind of error. Okay. So for example, this is your experimental point, right? And this is the point on your straight line, right? So this distance is like an error, isn't it? This distance is like an error, right? So what you do is you take the error square. When you square this for every point got an error, right? You take the error and then you go and square it. So all the error square, you go and square it and you go and sum up. Okay, so error square and you go and sum up. Now error square means something like this. This is your error square, and then you go and sum, right? And then what you do is that inside your mind, you go and minimize this sum. You see, you minimize the sum. All right, so in your mind, you are doing that. And from this minimization of this sum, it actually tells you how to draw your straight line so that your sum of error square is minimized. See? So that's how it is done. Cannot. Okay, so therefore we say that we want to minimize the sum of the square of errors at the points. All right, hence the term least square. Minimize means least, right? And then sum of the square of error. So the square here means square, right? So that's why we call it least square law. So that's how the term comes about. Okay, now. Okay, yeah? Okay, right. So this polynomial, we don't call Pnx, we call it Pm, okay? So this is the least square polynomial of degree m. And as you can see, our m actually is much less than the number of points given. Okay, then like for example, just now I draw 4 points, right? But my degree is not 3. My degree is not 3. My degree is only 1. Yeah, so you can see that the degree is much less. Okay. Then of course, what is the problem? What is our problem? So our problem actually is to go and find this Pmx. Now, of course, the question will tell us the degree. Okay, so the question will actually say, oh, you go and find a least square straight line, you go and find a least square degree 2 polynomial, and so on. Okay, yeah. So this is the least square polynomial of degree m. In general, it has this form. Okay, constant x to the power m, constant x to the power m minus 1, until this term is a constant term. Okay, yeah. So here, all the coefficients are currently unknown, and you have to go and find it. Okay, and if you can get the coefficients, then you substitute here, and that will be your answer already. Okay, so now the question is, how do you get these coefficients? Now, the coefficients are actually obtained by, there are m plus 1 of them. So they are obtained by solving simultaneous equations. These equations are called normal equations. And these are the equations. Okay. You see, here how many equations do we have? Here we got m plus 1 equations, right? Yep. Well, because you got m plus 1 unknowns, so you need m plus 1 equations to solve. All right, so the highlighted one, you see all the A0, A1 until AM, these are your unknowns. Now, of course, you also see other things. You see all the S, right? S0, S1, all that, right? And you see all the B, right? All these are what? All these are numbers. Okay, they are numbers, they are constants. But you need to calculate them. So actually, SK has the meaning of sum of x power k. Your xi is the x coordinate, the x coordinate of every point. You go and power k, then you go and sum up. And then the bk there is a summation of y x power k. So y is the y coordinate. So x is the x coordinate. Okay, so these are your sk and your bk. These are definition. All right, so what we do is that we go and calculate the sk and the bk. Then you get all the numbers already, right? Then you go and put into your simultaneous equations. Then you go and solve them. Go and solve for A0 until AM. Right? And after solving, then you put inside here and you get your answer. Okay, so that's least square polynomial. Is that okay? All right. Any questions so far? So far, okay, right? Yeah. Okay, so then let's go and look at our tutorial problem. Yeah, so we are doing this one here, right? Okay, so use the method of least square. You want to fit a parabola to the data. Parabola meaning degree 2. Okay, so degree 2. Least square. So least square degree 2 polynomial. All right, so this is the data given. All right, so let's see how we do that. So this one is number 4, right? Yep, so this is number 4 here. Okay, here, let me show you a different method. All right, here I don't deal with x and y directly. Of course, we can deal with x and y directly and just apply not this file, and then just apply all these things. Okay, we can also go and solve the polynomial, all the simultaneous equations. But here, let me show you a different method where I don't deal with x and y directly. But I do a translation. Okay, so I translate the x. You see, I put x minus 4, right? And I call this u. So this u is like my new x. And then my y, I also translate. I put y minus 7, and then I call this z. So z is like my new y. Okay, and I'm going to write down this degree 2 polynomial. Okay, so this is the degree 2 polynomial here. So y, so this is actually my new y, right? So it's like y equal to a0 plus a1x plus a2x squared. Just that your x is the new x, your y is your new y. Okay, so this is what we have. This is our least square parabola. Okay, so after this, I need to explain to you why we put x minus 4. Why I put x minus 4? First of all, this 4, what is this number 4? It's actually the mean of x. Okay, you see all this x, right? Minus 1, 1, 3, 5, 12. The mean is 4. Okay, and I put x minus the mean. And you still remember x bar, right? X bar is like the mean, right? So x minus the mean. If I do this, I can ensure that later on, my S1 will be 0. Okay, I can ensure that S1 is 0 later. All right, and then I can simplify my normal equations, make it easier to solve. All right, so that's the only purpose. That's the only purpose why we do this. All right, if you don't think that you want to simplify your equations, in fact, I think your calculator can solve 3 equations simultaneously. Then you no need to do this. You can still deal with your x and y. No need to do this. All right. Okay, then the next thing I want to explain is this y minus 7. What is this 7? Is it the mean of y? No, actually it's not. This one has nothing to do with the mean. I just go and pick the y here. Yeah, I just go and pick the y from the table. And then I see that, oh, there's a 7 here. And there's also a 7 here, right? So therefore I see, oh, I got 2 7. So I pick 7. Because if I do this, then later on, I take y minus 7, I will create 2 zeros here. There'll be a 0 here, there'll be a 0 here. And 0 can be useful because you will see 0 times anything also 0, right? So then I think, well, maybe it will help me to simplify. Okay, so that's the only reason. No other reason. Then of course, if you ask me, hey, can I don't put 7, I go and put y minus 5? Yeah, sure, you can do that. All right. Okay, then after doing this, I'm going to write down my normal equations. Okay, normal equations. I see this one is our normal equations, right? On your left side. It actually has a pattern. There's a pattern. Now, first of all, you notice that I have 3 unknowns to solve. My unknowns are A0, A1, A2. All right, so I know I need 3 equations. I need 3 equations because there are 3 unknowns. So therefore, you see, I write down 3 lines, right? Then A0, A1, A2. See, I write down 3 lines. Then after that, I'm going to put in the coefficients. Now, the right-hand side is easy. It's just B0, B1, B2, right? So this one is easy to remember. B0, B1, B2. And then I'm going to put in the coefficients to the A. All right, now first equation, the A naught is S naught. S naught, and then every time add 1. S1, S2. Okay, when you come to your second equation, now you add 1 from above. All right, so S1, S2, S3. All right, and then this one is S2. Can you see there's a pattern? S3, S4. All right, see, now you got your normal equations already. All right, and then you just go and calculate your S0, S1, S2, S3, S4, B0, B1, B2 according to this formula. But of course, now in your formula, you need to change. Instead of X, now you will change to U. Because now this is your new X, right? Instead of Y and X, now it will become what? Your Z. And then your X is your U, right? U power K. Is that okay? All right, so it's like this. So then you go and do up the table. You do up the table, you need your XY, then you need to calculate your UZ. Then your S square is sum of these. See, you need all these things, right? So when you do up all these, right? And then when you sum up, this is your S1, this is your B0, this is your S2, and so on. And as expected, your S1 is 0. Okay, so this will happen if you take X minus its mean. Okay, not? Okay, yeah. All right, so you got all this already, and you will put into your this normal equations. All right. Okay, so this is your equation. And you find, oh, because S1 is 0, then you see, oh, now your equation is simplified. Yeah. So if your calculator cannot solve 3 equations, then you solve by hand. Then it's also easier to manipulate. So you go and solve. So you get your A0, A1, A2. All right. So that means you got your least square polynomial already, right? Okay. So your least square polynomial is Z equal to this, right? Okay. You put in your A0, A1, A2. And also your Z and your U, you put it back. Now Z is Y minus 7. Your U is X minus 4. Okay. So you put it back. And finally, you get this. Okay, so this is your least square parabola. Any questions? All right, any questions or not, class? Well, looks like no question. So everybody okay or not?
Professor, I don't have a question, but it's not about this. Yeah.
Then about what?
So in Euler method, I don't get why the exact solution is the Taylor series.
Euler method. Euler
Yes.
method is actually this Taylor series, but only take the first two terms, right?
Yeah, but I don't get it. Why? Why?
Huh? Oh, we truncate because the Taylor series is infinite number of terms, right? So we cannot go to infinite number of terms, so we only take the two terms in front.
No, but why is it the exact solution?
No, it's not exact.
I mean,
it's not exact solution. Euler method, in fact, all the methods that you learn, Euler method, what improve Euler method, all these methods, they are not exact. They just give you approximate solution.
Then how we actually finding the error?
The error.
Yes, the error.
Well, the error, we didn't cover that. But for this Euler method, the error will be the h squared term, right?
Yeah. So like so inside lecture, I'm curious how they just put the error number over there, but they didn't exactly tell where it came from.
The error is because for that particular problem, we know the exact solution. So
Wait,
that's
how are you supposed to know that?
Yeah, I mean, it's just an example, right? So actually in real life, you don't know.
Also, when we're doing equation that we don't know the exact solution, we can't get the error.
Yeah, you cannot get the error.
Also, over there, they just they have the equation and they just calculate the exact solution. They just compare with the whatever method where we are using, right?
Yeah. So in our lecture notes, is because we know the exact solution. So therefore, we can calculate the error. But in actual situation, we do not know the solution. So you cannot, you don't know the error.
Oh, all right. Thank you.
Okay. Oh, sorry, I overshoot the time. Okay, so we meet next week. How do y'all find numerical methods?
I mean, what do I don't really get the purpose of this, like the numerical method.
Numerical methods is that we are not able to
Is it because we don't know the exact solution, the exact formula? That's why we need to use this.
Yes, we are not able to solve analytically. And like if you can solve analytically, then you no need numerical solution, right? Because numerical solution is just an approximation. But sometimes the equation is difficult, right? You cannot solve it, right? But you still want to solve it, then how do you do that? So that's why numerical methods is practical.
Okay.
It's a practical way of solving. Yeah.
So,
of course, like one of you say, it's troublesome. Yeah, and it's troublesome. Yeah.
So can it solve every single problem using numerical method?
Yes.
So every single problem.
Then, like for example, our solving non-linear equation. That means the equation very complicated one, right? You don't know how to solve, right? Then you can just use your Newton-Raphson method to go and solve it. Yeah. So it's a troublesome, but it's if you have a clear mind, then it's easy to do. Right? You agree? If you have a clear mind, then it's easy for you to do numerical method. Your mind must be very clear. Okay. Yeah. So if you have a clear mind, you can do very well in numerical method. Because numerical method is like no tricks one, no tricks, very straightforward. Yeah. Okay, now class. So I meet you all next week. Okay. Yeah. Good night, everybody. Bye bye.
Prof.
Yeah.
I have one question regarding question 2B, because now there are actually the n number is not wrong, is it 3?
Hold on. You are talking about which one?
Question 2B.
Yeah, n is 3.
Check with you regarding question 2B part 1 for Lagrange. This part, the multiplication for the numerator is actually not only 2, there's 3, am I right?
You mean here the denominator got 3 numbers, is it?
Yes, yes.
Yeah, there are 3.
It's just the numerator is just everything except for x naught, and the bottom is just x naught on the left, and the others is x1, x2, x3 on the right after minusing off.
I'm not sure which one you're talking about. You're talking about L0.
Yeah, I think I got the idea of it. Now if I saw the solution, it's fine.
Yeah.
Okay, can. And thanks, Prof.
Okay. All right. So class, I meet you all next week. Okay. Okay. Yeah. So good night, class.
Thank you.
Okay. Bye bye.